Hey everybody, and welcome to another episode of the Filtra.io podcast. So, some of you might have seen that a few months ago I posted something about AI and Filtra and the Rust community. And basically, what I said was that what's going on in the world and in our industry right now with AI feels so much bigger and so much more important, really, than a lot of the conversations that we've been having. It really feels like AI is going to have a massive impact, right? I think everybody recognizes that. But it's very unclear where things are going, and there's a huge amount of anxiety that I think all of us as developers feel about this next phase and trying to guide ourselves through a transition. And so, what I said in that post was that we at Filtra were going to try and be a productive voice in that conversation. And so, really, what that means for us at this point is exploring because we honestly, like you, don't have a lot of answers right now. And so today's episode, I'm really excited about because I think it fits in to this kind of exploration and it fits in an interesting way. So the company that I interviewed is called Tracel AI. It was very interesting when I started asking around to see who in the Rust community was doing important or interesting things with AI. This name Tracel kept coming up, and I had a hard time learning much about them. But as I dug in more to what they're doing, I realized that what they're doing is very foundational, and it fits in with one potential thesis about what the future might be, which is going closer to hardware and doing more foundational work. So I'm really excited to share this conversation with you. We tried uh, very hard, Nathaniel, the CEO of Tracel, and I, to build up some understanding of AI accelerators and how you program them so that you as the audience can understand what Tracel is doing and why it could be so disruptive and impactful. And I just think this was a super fun conversation, and it also brought to light some really surprising to me insights about how enabling Rust can be for some of this foundational software in the age of AI. So I hope you enjoy this interview. If you want to see more like it, please be sure to follow and subscribe. And with that, here's my conversation with Nathaniel. I thought it'd be interesting if we started by just talking about um, kind of like what kernel languages are and kind of the fragmentation that exists in that ecosystem and the problems it causes for AI model developers. Can you speak to that?
Yeah, sure. Well, GPU programming is not very easy. You cannot just program in Java and TypeScript and all of those languages. You have to use special languages that are designed for GPU programming. Some of them are similar to C++, but you cannot compile it with GCC. So those are Metal. CUDA is actually similar to C++, but you also have shader languages like Vulkan, HIP, Web GPU, so WGSL. So you have a bunch of different languages, and those are to write kernel specifically. And in an application that you want to leverage the GPU, you normally write the application in Python and C++ and whatever language you're used to for the CPU side of things. And then you embed those GPU kernels into your application.
Okay. Um, so yeah, you mentioned like this is like CUDA, which is something people have probably heard about because that's NVIDIA's big advantage, or one of them, I guess. Uh, and so that ecosystem is very, I guess, fragmented is the word I would use. Um, can you explain like why that's a problem for developers to have all these different languages?
Yeah, like for CPU, we're pretty used to using general purpose languages like Rust, Python, JavaScript, all of those languages. And if you want to deploy them, well, it's quite easy. You can just take the same application, deploying into an Intel CPU, an AMD CPU, even a CPU 10 years ago will work just fine. And most of the portability stuff is done by runtime, just-in-time runtime, similar to the Java runtime, or compilers like NLVM and all those things. So essentially, you write your application once, and then you can deploy to any kind of hardware you want. For GPU, unfortunately, it's quite hard because you need to take, well, you can take a portable GPU language like Web GPU, but you're not going to be able to leverage all of the special instructions that the GPU actually has. So if you want to leverage all of those performance benefits, you need to use hardware specific languages like CUDA for NVIDIA GPUs. If you want to target Mac GPUs like Apple Silicon GPUs, you need to use Metal. If you want to target Androids, you need to use Vulkan. So, and Vulkan has multiple actually GPU languages. So it kind of is pretty hard to do multi-platform GPU code. And that's the biggest problem for developers.
Yeah. So like every developer, if they want to run the same model on multiple GPUs, they have to rewrite those kernels, right?
Yeah, especially if it's different vendors. Like if you want to deploy to an NVIDIA GPUs and then you want to deploy the same model to an AMD GPUs, the GPU code is not portable. For a single like NVIDIA GPU, most of the time the kernels are portable, so you can deploy on different GPU kinds, but with the same NVIDIA platform. However, you're not gonna get the same performance because even the kernels, so the algorithm needs to be tailor-made for those hardware. You need to know how the hardware is actually made, so the hardware properties, so that you can optimize your kernel.
Right. This is super interesting to me. One thing that just occurred to me, there are chips that are not GPUs. There are like Google's TPUs and other AI specific chips. Is that different or is that the same? Are those also kernels that you write for those?
A lot of those specific processors are not necessarily programmable. So NPUs are quite hard to actually program. They don't have those like shader languages like GPU. It's not true for all. So I think Google TPUs has Palace. I'm not sure if it's the right name, but they has one Python DSL that you can use to program those chips. But normally you have to just configure a compiler. So it's not even assembly, it's lower level than that. You have to plug into their oftentimes proprietary compiler. So you have a high level algorithm, like I want to do a matrix multiplication on that chip. You just tell it to the compiler to have the code written for you. It's not a programmable chip. That's what I mean by non-programmable chip. But yeah, otherwise it's pretty similar. Like a TPU has its own uh, way of being programmed, and you cannot use the same platform to write the code for all of those different hardware.
Okay, cool.
It's pretty messy.
So yeah. It's incredibly messy. And so that's why I got really excited when I started to understand uh, what you guys are building, what your team at Tracel is building. So one of these things is called kubecl, and I think it addresses a lot of these problems. Can you explain what it is and how it addresses those problems?
Yeah, kubecl is I could call it a Rust extension that allows you to leverage Rust to write GPU code or any AI accelerator code. We don't support all of the AI accelerators yet, but those our plan. So we would like to support those TPUs as well as GPUs. And with kubectl, it's really optimized for performance, so numerical computing performance. So it's a just-in-time compiler, so it's not a ahead-of-time compiler because you don't want to compile all of the different kernels variation for all of the different hardware. It's like gigabytes of pre-compiled kernels. So it's just-in-time compile, and it compiles code based on hardware properties. So you can actually use all of the hardware properties like how many streaming multiprocessor there is on my GPU right now. What is the warp size or plane size that we call? If you're targeting CPUs, how many threads you have available, how many cores. So all of those things, you can use those during the compilation, the just-in-time compilation. So the goal is that you can look into the current hardware and use those information to adapt your algorithm at just-in-time compilation time. So this is the biggest benefit of kubectl. So you write it once, and you also have access to hardware properties so that you can really tune your kernels for the current hardware, no matter what is the underlying shader languages that are used.
Yeah, this is really interesting to me. So, let me make sure I understand before we go on. So the so kubectl, you write everything in Rust, and then you compile it, but then the actual GPU specific logic that's not compiled until just in time.
Yeah,
Is that right?
yeah.
Okay.
So let's say
Um,
you're deploying a model, and then you want to execute the matrix multiplication. So a very common algorithm. Then at runtime, the first time you want to execute the matrix multiplication, your algorithm that you wrote will fetch the hardware properties, and then it will decide how many tiles you need to decompose the problem. So can you use tensor cores, and if yes, what are the sizes of those tensor cores? What is the precisions that are supported on the current hardware? And the goal is that it will find the best configurations possible on your current setup.
okay. Cool. So that's all stuff that you've written, and I guess you would you can call that like a sort of compiler that you've created?
Yeah, it's a compiler and a runtime.
Okay.
Yeah.
Compiler and a runtime.
Now you don't have to manage your own execution queue, your own memory allocation strategy, all of those things we handle as well. Because those also are not portable. So that's why we made a really easy to use abstractions that abstracts the runtime as well as the compilation bits so that you can just write your algorithm, send them for execution, and we're going to manage all of the portability issues and performance issues.
Yeah. Okay, that's super interesting. So, one of the things I'm wondering here is like, um, with the current state where everyone's writing kernels for each GPU that they want to run on, the reason they're doing that is because by writing these custom kernels, they can, optimize their kernels for the hardware. Um, and so, and of course, when you're training AI or doing inference, like any little bit of optimization is a huge deal. So they do it. Um, but with kubectl, they shouldn't have to do it. But how is there a way that kubectl can guarantee that it outputs the most optimal kernels for each piece of hardware? Like, how does that work?
Yeah, you cannot guarantee that. I don't think anybody can guarantee that. But you can actually write your own custom kernels with kubectl.
Okay.
And let's say the normal use case, you want to optimize an algorithm on CUDA, and you know the GPUs that are in your data centers. So you're really focused on those GPUs. You can hard code a lot of magic numbers, I would call. So how many tiles? What are the tile size? What are the precisions? can I do a double buffering here, or should I not do a double buffering here? So all of those decisions you take for your current GPU. But you can take those decisions too and you write the same algorithm with kubectl. And it's going to output the same code that you would write with CUDA. The difference is you can parameterize the same algorithm, so the block size, the tiling dimensions, the double buffering things, and then you can perform auto tuning. So you can do micro benchmark at runtime, and you can like using that you can say, okay, this is my algorithm for, and that configuration is better on my current hardware. So this is how you write portable optimal kernels.
Okay. Interesting. That auto tuning part, I don't know anything about that. Is that something that people do
Yeah,
already?
it's not new. It's quite popular. So you have your algorithm, but it's parameterized by some hyperparameter, and then you just perform a search. You search what best configurations of my current algorithm is the best for that problem size, so the tensor dimensions on the current hardware. And then how do you score your search? Well, that's by doing micro benchmark. So you micro benchmark the different algorithm, and then that's how you can actually rank those and just choose the best configuration.
Okay, cool. So
That's
that's
also
cute.
why just-in-time compilation is pretty useful because you're not sure until you execute it on the hardware which one is the fastest.
Oh, interesting. Yeah, I hadn't thought about that. Wow, this is all super cool to me. Okay, so that's kubectl, and that's one core piece of what you're building. But then there's another piece, and I think that kind of gets to another big problem that exists in the AI space, um, which is this problem of having different code for inference when you're doing it in the training context, versus when you're doing it in the actual deployed context, because like the chips can be different and all of this. So, can you explain kind of that problem?
Yeah, so let's say you're building a machine learning models to do, I don't know, image classification. You're probably going to train it on the cloud with NVIDIA GPUs because those are the most common. But then maybe you want to deploy it into a robot or a camera to do object detections, or even into a car, into um, a laptop even. So if you're in that setup, you have to write the training code for NVIDIA GPUs. And then if you want to deploy everywhere, you want to also implement the same model, but for different hardware targets. And this is not fun. This is not fun. Um, so that's one problem. Some of the current solutions for that are ONNX. So this is a serialization format. So you can take your Python code for training, you serialize it, and then you can load it into runtimes that are, let's say, optimized for a camera system, so for a CPU, for instance. However, the translation format is not perfect. All of the post and pre-processing are not working the same. You have to rewrite those for all of the different platforms. So it's just pretty painful. So the goal with Burn is that you can write your training code, all of your model logics, your pre-processing step, the post-processing step, and then you can just use the same code for deployment as well as for training, because most of the optimization that we're doing work for both scenario.
Yeah, that seems like a big deal. Like, is it the case that, well, obviously it's a big deal because if you have to rewrite the code, you know, that's extra work. But like, are there also situations where code will where things will behave differently in the training
Yeah.
context?
Yeah, it could be. Yeah, the translations are not perfect. Numerical stability is not the same across different frameworks, across different runtime. So it's always safer to deploy the same code that you wrote for training, for inference, because you're pretty much guaranteed it's not going to be buggy. You actually test it during all of the experimentations that you did. So that's nice. Um, but on top of it, I think like at some point in the future, we might want continual learning. So this is where model continuously learn. And it will be cool if they could learn when they are deployed on device. So you could have a model that always learns on your own laptop, on your own private data. And the toolings today are not like you cannot deploy PyTorch everywhere. It's Python. It's not gonna run well in production on a mobile phone, on a camera, on a robot. So I think it's better to deploy something with Rust. That's why we're building it in Rust. And then you don't have that separation between this is prototype code and this is production ready code. So all of the code that you write with Burn should be pretty much production ready.
Yeah, that's super cool. And I had not definitely not thought about continuous learning. That seems like I mean, I hear people talk about that as a potentially big deal for the future of AI progress. So that's really interesting that this could support that kind of thing. Um, so one of the things that occurred to me when I was researching is that, Burn is all in Rust, and it feels like the fact that you used Rust kind of allows you to solve this problem in a certain way. Is that right?
Yeah,
So
yeah,
how does that work?
it would be probably extremely hard to do with Python. Mostly because of Rust doesn't have a garbage collector. So we can really leverage the ownership rules to do a lot of optimizations that are not possible if you have a garbage collector. Because dynamically at runtime, we know exactly the lifetime of variables. So we know if a tensor is used for the last time. And this is very valuable because we can reuse the memory in place. We can fuse some tensors. So even though you're not aware of it when you write your programs, some of the tensor in your model are not going to be materialized in memory. They're going to be optimized with our just-in-time compiler. And this is very hard to do in Python because variables are cleaned up after a garbage collector pass. So that's pretty hard. And even in C++, uh, some of those variables are just cleaned up after a function is a variable goes out of scope within the function. So in Rust, it's even finer grained than that. It's when a variable is used for the last time, So we leverage that a lot to do most of our optimizations. And because of that, we can support dynamic graph and dynamic shapes while supporting all of those optimizations, which are normally only available in static graph or compile mode that we call in the Python well.
That's really cool. Um, it's always exciting to me when I hear something like this where the features of Rust actually enable some fundamental problem solving like this. Um, all right, you mentioned Python. So I'm gonna play devil's advocate here for a minute. So like a lot of the AI researchers, basically all of them, use Python all the time. And part of this is because of the Python ecosystem. Obviously, the AI ecosystem is kind of built around Python, but also, Python's very easy to write, kind of easy to prototype in, that sort of thing. And Rust is at least has the reputation of being harder to write. So I guess someone could say that this feels like it might be an uphill battle for you guys to get the model developers and researchers to write Rust. How would you respond to that? How do you think about that?
Yeah, I don't think Rust is that hard to learn actually. And based on my experience, so I used to do all of the machine learning work in Python, and I built a recommendation engine in Rust. And most of my time was actually trying to optimize slow Python code, doing some shady multi-processing, multi-threading in Python, trying to fight bugs in Python, runtime exceptions. So writing Python is easy. Writing reliable Python and think that you can ship to production is quite hard. So you're gonna spend a lot more time debugging your Python code than you would do in Rust. So in Rust there is way less debugging, and debugging is the hard part. So this is one reason why. The other one is you can use LLMs today. So you have big chatbots that can actually teach you a lot of the programming language fundamentals. So if you have a compiler error, you can copy paste it into ChatGPT and ask it to actually explain to you why you have this and how you can modify your code to make it work. So it's easier and easier to get up to speed in Rust uh, now more than ever. So I think that might remove a lot of frictions from changing from Python to Rust. However, it's true, a lot of the AI ecosystem is in Python. So if you want to just import a model that is built with Python, modified a few lines of code to test a new idea, and then rerun the same program, yeah, I think it's it's a valuable use of Python. You leverage the ecosystem, that's good. Um, but you can also do it in Rust, and the ecosystem is building, so there are more models implemented, more algorithms that are there. And if you're building something truly new, there isn't a lot of ecosystem that you can rely on. And I think you're going to spend way less time debugging your Python code than you would do with Rust. So I think in those cases, it's great to switch to Rust.
Yeah, that makes sense. You answered that very well. And I think the AI piece, using LLMs to get up to speed in a new language, it's so interesting. I don't even totally know how to think about it. I think that's going to change just a lot of programming.
Yeah, and LLMs are pretty good at translation too. So I'm my native language is French, so it's very easy to take an English text and translate it to French because oftentimes we need to do both text when we do like job posting or stuff like that. So AI is very good at translation. And it's the same with code. So you can pass it Python code, translate everything to Rust, and then there is a good chance it's gonna work. So the programming language boundaries and the cost of migrating from one language to another is going down. So I think last year at RustConf, Microsoft announced that they would rewrite all of their C++ code base to Rust. And they're targeting, I think, 1 million line of code per developer per month, or some crazy amount of lines of code like that, because it's AI assisted translation. So yeah, that's something to take in consideration.
Yeah, that's amazing. I saw a year or two ago there was a request for proposals from, I think, the US Department of Defense for a system that would translate all of their legacy C++ to Rust. And I remember at the time I thought, well, I don't think the LLMs are quite there. But now I feel like they could probably do it.
Yeah,
Um,
they're probably not there yet. But yeah, with a human in the loop, an
yeah,
expert, someone that is good at reviewing code and guiding the LLM, I think it speed up the translation process quite a bit.
right.
Yeah.
Um, and gosh, that's so interesting for your business where you are going to face this problem of getting people to rewrite their workloads in Rust. But like, I don't know, it might not be a problem at all, and it will be less and less of a problem. That's very interesting.
Something that is hard is when you have a lot of complex logic and really critical safety code to translate. That's where
Hmm.
the AI falls apart a bit. For low-level programming, AIs are not that good yet. So they do memory management mistakes, they do performance mistakes, they do a lot of those things. Um, so that's why like I don't think we're gonna see like Unreal Engine being rewritten fully in Rust anytime soon. They have a huge C++ code base and it's very complex code. Same thing with PyTorch, so it's mostly C++ and Python. I don't think they're going to be able to rewrite all of those things in another language. But like small models in Python that takes a few thousand lines of code, it's quite easy to translate. This is high level code. High level code is easier to translate than low level fundamental code.
Yeah. And then, so I guess the code that would be getting rewritten into Burn is, um, I mean, it's models, right? And so it's like setting up matrices and that kind of thing. Um, do you have a sense personally of if the LLMs are pretty good at writing that type of thing, or if they're not? Because I imagine there's a lot less of that in the training set than like web apps.
Yeah, I'm not sure, but I think they're probably pretty good because there is a lot of scripts on GitHub, some experimentation, some model code. So I think there is a lot of examples out there from small models definition to real projects. So yeah, I don't think LLMs are going to struggle that much with that.
Okay, cool. So something else that I find exciting about what you're doing is, the industry I think has just barely scratched the surface on like on-device AI or AI at the edge. And I feel like that's going to be a much bigger thing, running kind of smaller models on devices. And it seems like the kind of the combination that you've chosen again of building Burn on top of Rust, it feels like that would have a lot to offer, especially where, as we talked about earlier, you don't have to rewrite, inference for every device that you want to run on. So is this something that you guys are excited about?
Yeah, yeah, obviously, and I think on device is pretty much the future because it's probably the most energy efficient way of deploying AI. So having only one big chatbot in the cloud is better than not having it. But at some point, it's going to be okay, which kind of AI you should use depending on the problem complexity, because the it consumes a lot of electricity. So in the future, if we want to reduce that consumption, maybe your small request is going to be processed on your phone, and then for the very complex task, they may be routed to the cloud. So I think we're going to see a lot more AI being deployed on the edge because it's the most efficient thing to do.
Right. Um, it almost feels like a decent amount of the chips are there in our devices now, but aren't being utilized that much.
Yeah. Yeah.
Um, so uh, different topic, but we discussed a lot of kind of the advantages of Rust. Well, actually, let me ask this before we change topics because it is about advantages of Rust. Does Rust itself make it easier to do this kind of cross-platform thing where you're deploying on a bunch of edge devices without doing rewrites? Is there anything specific that Rust brings to that problem?
Well, for the CPU side of thing, it's pretty portable. So you can compile Rust to even WASM, so you can deploy it into uh, browsers, which is not something you can easily do with Python. You can also deploy it to even some microcontroller that don't have an operating system. So that's pretty crazy portability aspect with Rust. And because of Cargo, so which is the packet manager and the building system of Rust, it's very easy to do all of those things, which is pretty hard to do with C++. You can do those things with C and C++ too, but you have to do your CMake script and your make script and all of those things because underneath that's the same LLVM compiler. So it's LLVM that can target all of those platforms. So Rust makes the CPU side code pretty portable very easily because of Cargo. And with kubectl, we're making the accelerated code, so the GPU code and the NPU code and all of those AI accelerator code portable as well with a just-in-time compiler. But it's not native to Rust, I would say.
Right. That makes sense. So what about the kind of numerical computing part of the problem? Does Rust give you any advantages for that specifically?
Hmm. Um, I don't think there is huge benefits of the Rust syntax for numerical computing, though the macro system of Rust, so the meta programming of Rust, is extremely useful to write those kernels. So we use a lot of macros, procedural macros, to actually write those algorithms as fast as possible. So in C++, you have const expression with templating. With the proc macro of Rust, we were able to kind of simulate the compilation time thing that Ziggs is actually doing with comp time. So we're able to simulate the Zig meta programming approach with proc macros in Rust. So I wouldn't say it's specific for numerical computing, but it was really useful to actually build the infrastructure that allows numerical computing.
Yeah, that's very cool. Um, so okay, we've been talking very technical. I'm going to take us up a level. Um, so Burn and kubectl are both open source. Tracel is a company. So this always raises questions about the business model. What does the path to revenue look like for you guys?
Yeah, we're making a cloud platform to help our users train and deploy their model. So it's called Burn Central. It's not like fully announced yet, but it's not hidden as well. So yeah, it's the cloud platform where you can deploy your model for training. You can monitor all your experiments. You can monitor your deploy model. If you deploy on device, you're gonna know all of the analytics where you deploy your model. So it's pretty much complementary to the open source code. So we're not making any private closed source extension to the core of Burn and kubectl. Those projects are open source as they should, and we're making a cloud platform on top of those two projects to help businesses to actually, leverage all of the code base that we did. And yeah, so that's pretty simple actually. That's similar to a lot of open source companies.
Yeah, it's the classic open core model,
Yeah.
right? Um, well, cool. That's very exciting to hear. What are you gonna, or what are you hoping will draw users to the platform?
Uh, they're just going to save so much time. Some of our users are not necessarily infrastructure engineer, so if they want to rebuild all of their AWS deployment script, all of their CI/CD script, if they want to not do all of those things, they're going to be way better off using our services compared to doing it themselves. It's going to be cheaper for them and it's going to be more reliable. So there are a bunch of reasons, mostly reliability, speed of execution, and it should be cheaper overall than building it yourself.
Yeah. Are you looking at building features that will support kind of the porting from training onto devices like we talked about?
Yeah, we kind of made our own model packaging. So when you package your model, it's independent on where you're going to deploy it. So normally in pretty much any software that you deploy in the cloud, you're going to do your own Docker image, and then you're going to fetch your own operating system, your own driver dependencies. We're abstracting all of those things. So you can deploy just the core of your models, and then we're going to automate all of the packagings for all of the different devices and make sure it runs at optimal speed without having you to become an expert in DevOps or MLOps or anything like that. You can focus on the machine learning part. We're going to automate the MLOps part.
That's very cool. I I think that could be a very compelling product for a lot of companies.
I would use it. I wish it existed when I was doing machine learning training and deployment before I started working on Tracel. So
Yeah. Um, so actually another question about the platform. Who are you thinking will be your customers? Because I'm imagining it's probably not like, OpenAI, xAI, Anthropic, like the big labs. Is it kind of a level down from that, or who are you thinking about?
uh, I cannot predict all of the future, obviously, but right now we're really going to support our open source users. So if you're already using Burn, for prototypes and you're thinking of deploying it to production, using our platform would be probably the best thing you can do. So we're really going to support our open source community first, and then in the future we may see if we cannot focus more on a vertical, on an industry, and really go that way. And if in our community we have people from OpenAI, from Anthropic, they're free to use the platform too. So
Cool. Um, so since you mentioned the open source community, what does adoption look like within the open source community? Have you seen people building some noteworthy projects with this?
yeah, we have people, especially in the open source, since we have a lot of users that are building private models, which is totally fine. But there are some open source projects that are using Burn, that are pretty interesting. Some were research project made by some researchers at DeepMind. Some were made in products, so privacy-centric products. A lot actually have like the if I can summarize, most of them they have requirements on where they want to deploy. So most of them want to deploy their own model on different kind of devices. So this is where the on-device aspect of Rust is really a key differentiator for Burn. And they train the model and they want to deploy it on any kind of devices. Yeah.
Yeah. Well, I'm excited for you guys. So actually on that note, have you had any big milestones lately as a company, like product breakthroughs or I don't know, revenue achievements or maybe fundraising, anything like that?
Well, we released Burn Central alpha, a closed alpha. So if you want to access it, you can actually send us an email and we can send you an access key. So we released it last month, I think, around that time. And we're iterating with early users to fix the bugs and to improve features. We also did the 0.20 Burn release a month ago, I think. It's early this year. And the biggest milestone was actually the CPU support in kubectl. So because kubectl before was only targeting GPUs, yeah, at the beginning it was actually a web GPU runtime only. And
Um,
then now it's extended to CUDA, to ROCm, to Metal, to Vulkan. So we have more GPU support. But we recently added the CPU support in it, and we proved that we can reach state-of-the-art performance with the same kernel. So you can write your same algorithm for pretty much any kind of accelerator you want. So that's a pretty key features. I don't know any other like numerical computing language that can do that as well as kubectl. So yeah, that's pretty great. Not all kernels are like perfect, so we're iterating on it, but it's the proof of concept is there.
cool. So, as far as the company goes, t tell me a bit about the team. How many people do you have on the team?
We're currently 8 people,
Okay.
quite a small team.
And is it very technical, I imagine?
Yeah, yeah, it's still very technical. Yeah.
Um, how did you come together? Like, how did the company even start?
Well, it started from a pet project of mine. I was working in a startup, so facing all of the problems I'm trying to solve right now. So I know them well. And I actually co-founded Tracel with one of my close friends from university. I met him the first day of my undergrad, so that's nice. And so yeah, so we are two co-founders of the company, and then I bring some of my friends from my masters, and then it grew with some people along the way.
Yeah. And are you guys hiring right now?
Yeah, yeah, we're hiring.
Okay. So, obviously our audience is lots of people who want to build stuff in Rust. So tell me a little bit about what you're looking for in engineers.
Yeah, we're looking for technical people that are pretty comfortable reasoning from first principles some of the problems, because we're building a lot of low level code, and you need to understand how the CPU work, the GPU work, and all of those things. and you can design algorithm based on that. So we're not looking for the most experienced person in the room. We're looking for the one that is actually able to do problem solving from first principle. So, and right now we're pretty much focused on hiring people in Canada. So I know it's not perfect, but for financial reasons, it's easier for us to do that. So if you're in Canada and it fits your description, you can submit your resume to our website. So that's pretty easy to do.
That's cool. I mean, I'm saying it's cool because I think if you were a Canadian that fit this description, that's a pretty awesome opportunity to go after. Are you in person in Quebec City then?
Yeah, yeah, we have an office in Quebec City, but we have also people working remotely from Montreal and other places.
Okay. So both of those are options.
Yeah, yeah.
Okay. Um, and tell me just to give a feel of like what working there is like. Like what's an interesting problem that you or your team got to work on recently?
Um, right now we're actually optimizing flash attention, so for LLMs. So we're writing all of the algorithm in kubectl with the goal to run at optimal speed on any kind of GPU and CPU with the same core algorithm. So that's pretty nice. We're also optimizing compilation time of burn because one of the drawback of Rust is that it's pretty long to compile, and especially if you're doing experimentation, the time it takes between your experimentations is pretty annoying. So we're working on optimizing Rust compilation time of burn. So we did some proof of concept. I think it's gonna be great. Um, yeah, so those things. I'm also working on device communication, so how to optimize lazy execution of tensor operations and how you go from a mutable, not a mutable, multi-thread space that is read-only to a mutable state that you can do all the optimization. So it's asynchronous channel optimization, I would say. We're also working on memory management optimizations. So a bunch of things.
Yeah. Sounds like plenty of interesting problems to sink your teeth into.
Yeah.
On the compilation optimization piece, because I know this is a common problem for a lot of people, are there any things that you've learned that, like any tips or tricks that you think people should know?
Yeah. The amount of generate of code that you generate is actually the biggest factor. So if you generate 50 megabytes of LLVM IR code, it's going to be longer than if you generate less. So if you use generics, which increase a lot the amount of code you're generating, it can drastically increase the compilation time. So that's similar with templates in C++. So you have to be careful with that. I know in Rust you can have like zero cost abstractions with generics, which is great. But a good thing to know is when not use those, because sometimes the performance is not really important in some places in your code, and then you can save in compilation time. Some other aspect is how you split your projects, so how you split your crates, your library, and how you manage your dependencies can actually improve a lot the compilation time. Because, and I learned that recently, and it's not yet implemented in Burn, but if you don't leak dependencies in types, it can drastically improve the compilation time because the Rust incremental builds actually detects those things. So yeah, so those are the two things to look up to. Yeah.
Helpful information. Um, so is there anything unique that you would point out about like the culture at the company?
Something unique. I think we're funny. So we're laughing a lot in the office and we with each other, and we're not afraid of tackling very hard problems. So we have, let's say, I think it's important to keep that along your career. It's the beginner mind. So
Hmm.
you see a problem, oh, let me learn that and try to solve it pretty quickly. Don't be afraid to actually go and learn new things. So that's pretty that's what we are as a team. So
Yeah. Funny's good. I I think that makes a big difference when you're tackling hard problems, being able to
yeah.
laugh a little bit.
Yeah, we're
Actually,
not like we're not depressed. Like some may be depressed because "Ah, it's so hard, never works." But no, we're going the other way. We're laughing at it when it's hard.
awesome. Uh, since I'm imagining you telling jokes to each other, this made me realize, do you guys speak English or French in the office?
Most of the time it's actually French, but
Hmm.
sometimes it's also English. But the French in Quebec City, especially with people in computer science, it's pretty French English. So it's
Oh,
French. Yeah,
yeah. You're using all the English names for
yeah,
packages and everything. Yeah.
yeah.
Okay, cool. And to that point, I guess, you're in Quebec City. Um, I'm curious what the tech ecosystem is like there. I don't hear of a ton of startups coming from that area, though I realize um, there's a lot of technical talent there, right?
Yeah, there is. There is. No, there's a lot of people that are actually technical in Quebec City. I think it's a city close to 1 million people. So it's not like a small place. It's not as big as the biggest cities like Montreal and Toronto, but it's also not small. And yeah, there are also a good amount of people that are like the normal engineering field, like optical, mechanical engineering. So a lot of those things here. Lots of good people in physics and electrical engineering. So we have strong people in those fields, and some of them actually transition to software engineering, and they're pretty good also at low-level programming. So yeah,
That's
and
very
there are
cool.
startups. There are startups too in Quebec City. The ecosystem is not that bad. Yeah.
Yeah. Are your investors primarily from that area as well, or are they from all over the world?
No, they're from pretty much all over the world. Yeah.
Okay.
In the US and Canada, yeah, to be more specific.
Okay. North America. Um, all right. Well, that was all the questions I had for you. I really enjoyed hearing about what you're doing.